Alright, so in this video I would like to explore how the current flows in a material. And in particular I'm going to derive a formula that relates a few different quantities together. So to begin with, I'm going to start with a claim. And the claim is that in a material the current density is going to be equal to some constant times the electric field. All right, so essentially what this is claiming is that if I increase the electric field that a conductor is exposed to, then the flow will increase, which seems sensible enough. However, there is a little bit that is mysterious about this, and it's not obvious that this should be true. In particular, the electric field should be related to the force, which should be related to the acceleration. But meanwhile, the current density is related to the speed. All right, so saying that something related to the speed is proportional to something related to the acceleration, that does not seem obviously true. In fact, that usually would be an incorrect claim to make. And your book goes into a fair bit of detail trying to justify this relationship. I'm not going to go into nearly as much detail as the book. Essentially, what the argument revolves around, though, is that the drift speed of the electrons is so small compared to their actual speed. The thermal motion of the electrons has them moving extremely fast while they are actually drifting relatively slowly. So that component of their motion is really, really small, and that's why the acceleration is not going to be determined exclusively by the electric field. Okay, so I'm going to just assume that this relationship is true. All right, so then what is this constant of proportionality then? This sigma is the conductivity. And unfortunately, we're using the same letter to mean two different things. So don't mix up conductivity with surface charge density. They are totally unrelated. This one is a material property. The other one depends on how the excess charge is distributed. So it's just a letter, and I don't want you to get confused that it's the same one that we used for something else. Okay. Another way that we write this exact same relationship, and this one tends to be more common, is that the current density is equal to 1 over rho times E. And this rho is called the resistivity. And again, we've used rho for a totally different quantity before. Before we used rho for the volume charge density. This is a totally different thing, again, than that. All right, so the relationship between sigma and rho is just that the conductivity and resistivity are reciprocals of each other. And in both cases, it's just a material property. So you could look up on Wikipedia or some chemistry websites or what have you, what is the conductivity for copper? What is the resistivity for bismuth? What is the resistivity for aluminum? Those are things that you can just look up and find a value for those. Okay, so what I want to do then, since the current density and the electric field, according to this claim, are in the same direction, is I'm actually going to solve for the resistivity. So resistivity is going to be equal to the electric field divided by the current density. Okay, and those are just the magnitudes because the directions agree, so I can get rid of the directions. Okay, well, I'm going to use a couple of relationships. So one of the things that we had was that the delta V between 2 points, the potential difference, is equal to the negative integral of E dot ds. But we're going to assume here that the electric field is constant. And if that's the case, then this is going to be equal to the electric field times the length of the object. Okay, so if I take some electric field and I move along it for some distance, then the potential difference is just the magnitude of the electric field times the distance, particularly if I'm just interested in the magnitude. So I'm ignoring the minus sign for now. We're not worried about whether it's positive or negative. Okay, so then rearranging this, the electric field is equal to the potential difference divided by L. Okay, the length over which the electric field exists. Okay, so that's one. And the other relationship that I'm going to use is the relationship for the current density, which is that it is the current divided by the area. Okay, so I'm going to plug these both in, and I get rho equals, well, E was delta V over L, and J is I over A. All right, so doing some algebraic rearrangement, which you can double check on your own, I get rho L over A equals delta V over I. All right, so this relationship is going to be one of the most important relationships that we use in studying electric circuits. All right, so let's look at the different parts of this. Well, one thing to notice is that this thing that's on the left-hand side, that is all just the dimensions of an object, its length and its cross-sectional area, and the resistivity, which is a material property. Okay, so this all just has to do with the material and the object. And then on the right-hand side, the potential difference and the current, those things, let me use a different color, those are all macroscopic. So it turns out that we can just measure a current, we could just measure a potential difference using handheld devices. Those are things that we don't need some sort of, atomic understanding in order to tell what's going on. All right, so the stuff that is on the left-hand side, we give a name to. R equals rho L over A. All right, and here, R is given the name resistance. And remember, rho is resistivity. All right, so while resistivity is a material property, resistance is not. Resistance depends on the specific object. All right, and we will return to that later, but for now, you should think of resistance as corresponding to a specific thing. It isn't a general fact of nature. You can't go on the internet and look up the resistance of a material, but you can look up the resistivity. Okay, so now I want to talk a little bit about units. So the units of resistance are what we call ohms. So the symbol for this is an omega, which is this horseshoe shape, and it is pronounced ohm, O-H-M. So the name is kind of a pun on the symbol omega, ohm, and it's named after a scientist, Ohm, so that's where that comes from. Then, based on that, we can figure out the units of resistivity, which up to this point I haven't told you. So units of resistivity, well, in the formula, if I take a resistivity and I multiply it by a length and divide it by an area, I need to get ohms. So you can then figure out that the units for resistivity are ohm meters, which you should think about in terms of the fact that it needs to cancel the meters in the length and the meters squared in the area, so we just have 1 meter left over. Okay. There is no special name for ohm meters, and if you wanted a unit for conductivity, then it would just be 1 over ohm meters. So that's, fairly common. All right, so I'm going to use this relationship, R, to simplify this formula that I outlined in blue. So essentially, what I'll get then is R equals delta V over I. All right, so you can see I just took rho L over A and replaced that with R. All right, so this formula is known as Ohm's law. Okay, again, discovered by Ohm. And if we think about what this means in terms of some material, well, remember, a potential difference is just something we can measure, and we can choose what a potential difference is between two different points on an object. We have devices that can do that. So if there's a larger delta V between 2 points on an object, that means that we're going to have more current. So the larger the potential difference, the more current is going to want to flow. If we have a larger resistance, that means that we're going to have less current. So we can literally think of the resistance as how much the material resists that current. If we have something that's really good at resisting current, there will be less current. If we have something that's really bad at resisting current, then it'll have more current. All right. And so in some ways, this formula is a definition of resistance. So we could take any object, we could apply a potential difference, measure the current, and then the ratio is a resistance. So Ohm's law defines resistance. So in practice, we would measure a resistance and then use the dimensions of an object to calculate the resistivity, which you would then publish. Okay, so this is the order you would go in. You measure delta V, you measure I, and then use it to get R. We can also think of this as sort of a cause-effect relationship. So if I rearrange Ohm's law a little bit, then I get I equals delta V over R. Okay, and this is, as I said, more of a cause-effect way to think about it. Essentially, the stuff on the right-hand side I set. So I take some object which has a resistance, I apply some potential difference to it, and then at the end of the day, the result is that there is some current in that object. And so the stuff on the right-hand side is the cause, the stuff on the left-hand side is the effect. So that's another way to think about what Ohm's law is telling us. And then finally, the way I actually remember Ohm's law is the other arrangement, so delta V equals IR. This is a pretty common way to write it, although all the other ways are pretty common as well. I personally think that it's easier to remember a formula if you don't have to remember which thing's on the top and on the bottom. So delta V equals IR is the place where they're all in a line, and so you don't have to worry about division. Again, all these are equivalent to each other, and there are a couple of different ways to think about what's going on in this rule. But Ohm's law is going to be a big one that we're going to use for the next few chapters.